Now that we have an understanding of the interiors of the terrestrial worlds, we can move on and begin examining their surfaces. We're going to see a wide variety of terrains and features, but amazingly, these can primarily be explained by four processes that occur on the terrestrial worlds. We'll be examining each of these in some detail. For now, let me list them: impact cratering, volcanism, tectonics, and erosion. Each of the terrestrial worlds has a varying degree of each of these, and of course they operate under various conditions and environments. But primarily all that we see on the surfaces of the planets is shaped by these four processes. When we consider impact cratering, we need to go back to the beginning of the solar system. We had explained that the planets were formed by impacts of planetesimals accreting into larger bodies, and the final stages of this definitely left their mark on the terrestrial worlds. Two of these worlds, our Moon and Mercury, still bear the scars of this early stage of impact cratering. But over time, the rate of impacts greatly declined until it's very, very small today. The result was that small craters greatly outnumber large craters, and interestingly, the size of craters depends greatly on, number one, the size of the impacting object, number two, the velocity of the impacting object, and number three, the composition of the impacting object. You can imagine that as these objects would strike the surface, matter would be expelled. You'd end up with a bowl-shaped depression, and again we see exactly that on the surfaces of these worlds. However, planetary scientists can make use of the fact that craters normally would remain on a planet unless they are reworked by another process of the four. So in other words, on the Moon and Mercury, where the other processes don't operate very much at all, the craters are still evident. And therefore this is considered a very old or ancient surface. Many of the original craters are still there today, not having been changed. What about on Earth, Venus, and Mars? Well, here the other three processes, again volcanism, tectonics, and erosion, begin to slowly, gradually erase these craters. And as a result, scientists can use this technique of looking at the craters to see how much they have been changed to get a relative idea of the age of the surface. If the craters again are still clearly pristine, we know it's a very ancient surface. They've not been changed much. But if the craters are gradually or completely obliterated and reworked and covered over, we know that's a younger surface. And we see this very clearly, again, on Earth, Venus, and especially Mars. Let's move on now and discuss volcanism for a few minutes. We're all probably familiar with perhaps pictures or videos of volcanoes here on Earth erupting lava out onto the surface. Here's where, again, deep within the Earth, great amounts of heat melt the rock. That heat creates great pressure, and finally that molten rock finds a weak spot in the crust and erupts onto the surface. This, of course, can have great effect on the surface, filling in lower areas, building volcanoes on some planets. But there's another feature that's very, very important for us to understand, and that is that volcanoes not only give off liquid rock or lava, but they also expel gases into the atmosphere. And this can have tremendous long-term consequences on a planet. Moving on to tectonics as the third type of process that modifies the surface of a terrestrial world. Tectonics really refers to tremendous forces beneath the surface that affect the surface. We see in our diagram here an image of the interior of Earth, and you notice there are some circular cells beneath the surface, reaching down deep into the Earth near its core, where the rock becomes very, very hot, and gradually moving towards the surface, rising. Notice that some of the cells may push the crust together, whereas other cells may stretch it apart. Well, this we call convection, when the rock is moving towards the surface, releasing some heat, and then descending back deeper into the Earth. Again, this convection creates tremendous forces or stresses on the crust, sometimes pushing it together, as you see here in our diagram, Oftentimes mountains will be pushed up because of this tremendous force. Other times the crust may be stretched apart, and we may get a valley or a large crack in the Earth's crust. Perhaps that crust may fill in with ocean water, but the point is the surface is greatly affected by this force. Two famous illustrations, as you see here on the left, the Himalaya mountains are being pushed up as India is pushing into Asia. They are growing taller each year. On the right, we see the Red Sea region. Here the Red Sea is an area where the crust is being stretched apart, and we have a much lower depression, which again has filled in with seawater. Our fourth process is erosion, and we're probably somewhat familiar with this. We see some images here of the Colorado River over long periods of time carving a channel which we know is the Grand Canyon. We think too of great glaciers in different parts of the world and how they have resurfaced different areas. It's also important to realize that wind can act as an erosional agent by gradually, slowly wearing away rock, maybe piling up in some areas, removing it from other areas. So I think you can see that erosion requires an atmosphere. Number one, an atmosphere is required to have sufficient pressure at the surface so that liquid water can exist. That's a fundamental requirement. It also is important, of course, for wind. And so erosion really only occurs on a planet that has an atmosphere. Well, now that we've seen the basics behind the four processes, let's go ahead and apply what we've learned towards each terrestrial world. We'll take a brief glimpse at each. We'll see how each process has affected that world, and we'll get a very nice big picture or context in which we can see each individually. Starting with our moon, probably familiar in just looking up at it, there's many craters there. So as we mentioned at the outset, here's where cratering was dominant, and really the other processes were not. Why is that? Well, you may recall from our previous lecture that the moon, being a very small world, lost its internal heat and therefore really doesn't have the energy to drive volcanism or tectonics. And so there's really no features on the surface that indicate these processes played any great role. Certainly there could not be any erosion, so we know there's no atmosphere on the moon as well. So the moon has a very ancient surface, heavily covered in craters, some areas a little more than others. Some regions there was a bit of lava that flowed over the surface when a large impact melted the surface, and this lava then would fill in the craters, and we see a little smoother region today, or a little younger region. But again, this is primarily due to the heat of a huge impact. And of course, being a small world, the moon again has lost its heat and is now geologically dead. Let's move on to Mercury, which has an appearance very much like the moon. Once again, a heavily cratered surface tells it's a very ancient surface. Many of the original craters still in place there. They've simply not been altered over time. We do see a few mild features, we might call them, that indicate some motion beneath the crust. Mercury, as you see here, has been known to have large, long cliffs, indicating some movement beneath the surface. This was almost certainly very long ago when there was still a little bit of heat left and drove this little bit of activity. Again, with no atmosphere, we certainly wouldn't expect any erosion there on Mercury, and with very little heat, there really wouldn't be much in the way of volcanism. There may have been a little bit early in its history, and we do see some areas where there is some lava flows, but again, this would have been very early and by now has long since died away. So once again, a smaller world having lost its internal heat, Mercury is quite geologically dead. Let's move on now to Mars, a fascinating planet, one that displays a great variety of features. In this false color image that you see here, we see, again, regions of great diversity. In the top, we see a false colored blue lowland region where it's relatively smooth, which tells us, of course, that some of the original craters have been erased. But notice in the left-hand image, these southern highlands, higher elevations, heavily cratered. And so again, we have just said, this would be considered a much older region with all of these craters here. And so there's quite a variety. Some regions of Mars more heavily cratered than others. Mars is well known for huge volcanoes, which clearly indicate that this was a very important process. But even in addition to the huge ones, there's a number of smaller ones as well. How about tectonics? Well, we see in the right-hand image a vast canyon system, the Valles Marineris, 2,500 miles long. This enormous crack in the surface, we believe, was caused by tremendous upwelling of material beneath the surface, and so this is clearly a sign of tectonics. And finally, we're going to see a couple pictures in just a moment of how erosion's taken place on Mars in two different ways. Here you see an image of some of the large volcanoes on Mars, 4 of the largest in the entire solar system. So this clearly tells us Mars has had an active past with periods of great volcanic activity. Now, being a medium-sized world, Mars by now has lost much of its heat, and we don't believe it is active today, but the activity may have lasted quite a long time until fairly recently. And in terms of our solar system, 200 million years ago is fairly recent. We mentioned the great Valles Marineris canyon system. Here you see an image of that in more detail, showing us again this tremendous rift in the surface of Mars, more than likely caused by, again, a great upwelling of material that cracked the surface open. Over time, different parts of those cliff walls might slump inwardly, as you can kind of see in the right-hand image there, and that would gradually enlarge the canyon system even further. So really some very dramatic, very huge tectonic features and volcanic features here on Mars. How about cratering on Mars? Well, Mars has quite a few more craters than Earth, but not nearly as much as the Moon or Mercury. So somewhat of an in-between case. And as we mentioned, there are regions of Mars that are heavily cratered and others that are not heavily cratered. So a great variety, as we just mentioned, in the highland or lowland regions. Great amount of variety. But interestingly, as we look at different regions that have some craters, we can again use that technique we mentioned before, carefully looking at the craters to see their condition. Are they still fresh, so to speak, and pristine and unmodified? Or, on the other hand, have they actually been modified, changed, worn away? Here you see a couple of images showing regions on Mars with some craters at various stages of decay. If you look down in the extreme lower left, we see a fairly young, fresh crater. This is what we would expect it to look like. But notice the other two images show craters that have begun to fill in with dust and other soil that's been transported there by wind. So this is a good example of wind erosion. Although Mars has a fairly thin atmosphere, it is enough to enable the transport of this material, and these craters can gradually be filled in, and in this sense then be considered as eroding. Our right-hand image shows a vast dune field on Mars where the wind has sculpted the surface here, and we see very few, if any, craters. So again, we do see this erosional process occurring on Mars, not nearly as strongly as on Earth, but over long periods it certainly has a tremendous effect. So this is the first manner of erosion on Mars, but you and I are probably more familiar with erosion in terms of water. Well, there's strong evidence that at one time Mars in the past had liquid water on the surface, but no longer does. Here you see an image showing just such a region that gives us this impression. We look down with orbiting spacecraft and we see ancient riverbeds, channels that almost certainly were carved by water. They have the exact same appearance as such features here on Earth. But how could we really verify that that's exactly what's going on here? Well, you may have heard that in recent years NASA has been able to place spacecraft on the surface of Mars, in particular roving spacecraft that are able to then travel to different regions and examine the rocks close up in detail. Some even able to drill into the rock, get a pristine sample, and analyze its composition. What have they found? They found rocks that only form in water. And so this does confirm that here on Mars we find regions where there had to have been liquid water in the past. This famous Spirit and Opportunity rovers did a tremendous job beginning 2004, and more recently NASA's Curiosity rover continues this task as it investigates a particularly rich area on Mars. From orbit, we can even look down with spacecraft and map different regions, composition, and see where some of that water may have gone. Now, much of it was lost from the planet, but there is still some that is basically buried within the soil as frozen water or ice. And so this confirms for us that, again, at one point in the past, Mars was a wet world, rocks formed in the water, and we see that left over today. You may recall we explained what happened to Mars. Remember, Mars' heat cooled off, its magnetic field weakened, and that left its atmosphere vulnerable to the sun's radiation. When the atmosphere was gone, Mars could no longer support liquid water on the surface. Finally, let's go ahead and take a look at Venus, another fascinating world with a rich variety of landscapes and terrains and features. Now, you recall that Venus is more difficult to investigate because of that very thick atmosphere. We can't just fly over and take a close look or even see it well from Earth, but rather we've got to send spacecraft to map Venus with radar. So the images you're going to see were taken with radar, and they require just a bit more interpretation. Here you see false color images in somewhat more detail than we saw previously of Venus' surface. Here the pinkish whitish regions are higher elevation, and the bluish regions are the lower elevations. Well, we see clearly there is at least one very large high elevation region and a few other smaller ones. But the remainder of the surface is relatively the same elevation, maybe some very mild or modest changes, but this in itself is a clue. On Earth and on Mars and even on the Moon and Mercury, we see more dramatic elevation changes, and yet it seems as if Venus' surface doesn't have such dramatic changes. Why is that? Well, it turns out that the answer has to do with the volcanism on Venus. Now, when we look through our radar images, we don't see very many craters. Well, that implies that something clearly must be erasing them. Certainly some of them are going to burn up. These impacting objects will burn up on the way through the thick atmosphere, but that doesn't fully explain the lack of craters. Instead, what really happened on Venus was that between 700 and 800 million years ago, there was a tremendous amount of volcanic activity. This activity spread lava far and wide over the surface of Venus, and you can well imagine that most of that lava would end up in the lower regions, filling in those lower depressions and making the surface seem as if much of it was of similar elevation. And that's exactly what we see. So we don't know every detail of this event, and we don't know every reason why Venus was particularly active, but it certainly seems, based on evidence from its surface, that it was a particularly active time on Venus when much volcanism was occurring. We see certainly today many volcanoes in these radar images, and other regions, again, that are greatly filled in with lava. So a very interesting puzzle for us to continue to work on the history of Venus. How about tectonics and erosion on Venus? Well, we've seen features through the radar images showing, again, the crust being stretched apart, the crust being pushed together, much as we described here on Earth, clear evidence for tectonics, and frankly, that doesn't surprise us, does it? When we consider that Venus is a large terrestrial world, nearly as large as Earth, we would almost expect it to retain a great amount of heat, and that there would continue to be a great amount of activity based on that heat. So it wouldn't be too surprising at all that Venus does have, again, a significant amount of tectonic activity, and again, we do see some features indicating that. Now, as far as erosion, this is, again, a very interesting, unique world in the sense that Venus, as you might know, has a very thick atmosphere. Now, you might think at first, well, that should mean a lot of erosion, but actually the atmosphere is so thick that the wind is not able to move very much, not very fast at all to transport material. And so there's very little, if any, wind erosion. How about water erosion? Well, of course, Venus is quite hot on the surface, and so we wouldn't expect any frozen water. But could there have been liquid water on Venus? Well, interestingly, we believe Venus started out very much like Earth, probably with oceans of water. And yet, the few images we have of the surface today show absolutely no water on the surface of Venus. Other evidence indicates that there simply couldn't be any. How can we say that? Well, I want to take a minute and share with you a little bit of the story of how Venus got the way it is. And I'll share with you a bit of a more detailed slide. You may wish to pause the video and examine it at your leisure and consider what it's really telling us. Venus' story really begins with the fact that it was clearly closer to the sun than Earth is, and naturally we would expect it then to be warmer, wouldn't we? Well, we think that early in its history, that closeness to the sun, that higher temperature, meant that much of Venus' oceans began to evaporate. Well, the high temperature, of course, would cause that to happen. Now on Earth you would say, well, that water would precipitate back out and fall back to Earth. However, at Venus' higher temperature, that water vapor effectively held in much of the heat and caused the surface to get even hotter. This is the greenhouse effect that perhaps you've heard about. This process, once it gets hotter, then evaporates more of Venus' original water, and the temperature rises even more. This process reinforces itself to the point that it begins to get so hot that carbon dioxide that is locked into the rocks of Venus begins to be released, or baked out, so to speak. Well, carbon dioxide is also a very powerful greenhouse gas. It also is going to hold the heat in and cause the surface to get even hotter. So now we've got virtually all of Venus water evaporated, holding in the heat. We've got carbon dioxide from the rocks added to this to hold in even more heat. That temperature is rising and rising and rising. Venus water is at a very high altitude in its atmosphere. What happens then? Remember a key point we saw in a previous lecture. Venus has a very slow rotation and as a result, a very weak magnetic field. We explained that that magnetic field protects the atmosphere. Well, with no magnetic field, Venus water was vulnerable. It was easily broken apart by the sun's powerful radiation. Much, if not all of it, lost to space. Very little left today. So we really see how this process played out and resulted in Venus not having any liquid water on its surface today. A very dramatic, different history than that of Earth. On Earth, although some water evaporated, the temperature was low enough that, again, it would typically precipitate back out and remain in liquid form on the Earth. So again, a really key factor here, that lack of magnetic field, that extra temperature, all of this conspired to basically remove the water from Venus. Quite an interesting story when we consider how that played out long ago, and then the volcanism of Venus also to shape the surface that we see today. Well, we've learned a great deal about the surfaces of the terrestrial worlds, haven't we? Let's go ahead and do our summary. We saw that there were four main processes that shaped the surface of a terrestrial world: impact cratering, volcanism, tectonics, and erosion. We saw that as far as the Moon and Mercury were concerned, really the dominant process there was cratering, wasn't it? Original impacts from the final stages of accretion are still in evidence today. Why? Because the other three processes simply didn't operate on these worlds. There really was no atmosphere to cause erosion. There was very little internal heat to cause volcanism or tectonics. However, when we came to Mars, we saw great variety in the landscape, didn't we? Some regions were heavily cratered, indicating they were still quite old, but other regions were far less cratered, indicating something had resurfaced those areas. What was that something? Well, again, we saw, number one, numerous volcanoes, including some giant ones. So Mars held onto its internal heat longer, and it was able to then have this tremendous amount of volcanism. No doubt much of that surface covered in lava to erase the craters. We also saw evidence of tectonic activity. And again, that didn't surprise us, did us, when we said Mars would hold on to its heat for some time, perhaps not all the way to today, but would hold on to that. We saw at least one huge canyon that occurred when the surface was split open. And so again, this tells us there was much geologic activity there. Finally, what about erosion on Mars? Well, we did see, of course, even today, wind erosion as dust and soil are transported in the weak Martian atmosphere. But what was real significant was we do see evidence of past liquid water on Mars. There's none there today because the atmospheric pressure is insufficient, but there's clear evidence not only in the features that we see, but when we've landed spacecraft, picked up the rocks and examined them, we find rocks that only could form in water. So clearly early in Mars history, it was a warmer, wetter world, much more hospitable, and yet it changed dramatically. Finally, we saw that Venus has few craters for several reasons. Number one, many objects would burn up in that thick atmosphere, but perhaps more importantly, the fact that Venus had a tremendous period of active volcanism, and much of the surface has been filled in with lava. There's really not much erosion there on Venus. That atmosphere is almost too thick. Very little wind can move any material about. And we also explored this whole issue with Venus water, didn't we? Venus started out with water, but its proximity to the sun meant that this higher temperature evaporated that water. That water now held in much of the heat in a greenhouse effect, driving the temperature even higher, baking CO2 out of the rocks, intensifying the greenhouse effect still further until all the water now is in the atmosphere. Why isn't it there today? Because again, the slow rotation of Venus means that there's very little magnetic field to protect the water from the sun's radiation, and therefore that water was broken apart long ago. So I think you can see the great variety of surfaces that we see among the terrestrial worlds, and yet interestingly, we saw we can explain pretty much everything we see with those four major processes, didn't we? So these are really the key to understanding the terrestrial worlds, their surfaces, their features, everything we see on them, we can usually attribute back to those four processes. So I hope you've enjoyed our two-part look at the terrestrial worlds. When we pick up next time, we'll examine some smaller bodies in the inner solar system, the asteroids.